Hey guys, this is Coach Lowe and this is Geometry, and we are starting Chapter 8 today, and we are going to talk today about geometric mean. Chapter 8 is right triangles and trig, which is one of my all-time favorites, so going to be totally fun in this chapter. And we're going to start with 8.1, which is geometric mean. Now don't read into this and think, oh, that means geometry is super mean. No, that is not what that means. All right. So let's define geometric mean. So geometric mean happens when the means, remember we talked about means and extremes, when the means of a proportion are the same number. So when I set this up, it looks like this. I have means and extremes. Remember we talked about the numbers on the outside are the extremes, way out. All right, so we talked about extremes being way on the outside, extreme. So stretching way out, and the means are in the middle. So you can see means are the same number, some number x. So that means when I, means, okay, so when I cross multiply, I know you don't appreciate my humor. I got it, I know. When I cross multiply here, and I multiply the means together, I get x squared. I multiply the extremes together, I get ab. And remember when I solve this, I get plus or minus, but we're talking about length, so we'll just take the positive. Plus or minus, again, just the positive square root of AB. So this is kind of where we're going to plant. We're going to use this. We won't derive it every time, but this is how we find the mean. Now, the reason why we're looking at this is because we're going to use this inside a triangle, of course. But let's just practice on finding the mean between two numbers. So I want the geometric mean, so not the mean like, you know, the average, but I want the geometric mean between 6 and 10. All right, so that means, remember, x equals the square root of a times b. So in our case, a will be 6 and b will be 10. So x equals the square root of 6 times 10, which is the square root of 60. Now, you may remember from the last couple of years, you could break 60 down. 6 times 10, 2 times 3, and 2 times 5. So you keep breaking these down until you have prime numbers. So all of these are prime. They won't break down anymore. And then I want to see if I have a pair. And I do. I have a pair of 2's. So that can come out as 1, 2. So I'm going to take a 2 out to the outside. And then let's put what's left on the inside here. So the things that I can't take out are a 3 and a 5. And I know that 3 times 5 is 15. So x is equal to 2 times the square root of 15. So when I'm looking at square roots, I want pairs, two numbers that have been multiplied together, perfect squares coming out. So the square root of 4 is 2. 2 times 2 here is 4. Square root of that is 2. The 15 has to stay inside because it is not a perfect square. Nothing in it is a perfect square. All right, let's get some theorems going here. So these are theorems that you'll need to put in your notebook. Theorem 8.1 says, if the altitude is drawn, we know what an altitude is, right? That's that line that comes from a vertex to the opposite side and is perpendicular to that opposite side. It measures the height. So if the altitude is drawn to the hypotenuse, so I'm dealing with a right triangle, to the hypotenuse of a right triangle, then the two triangles formed are similar to the original triangle and to each other. All right, so I'm going to show you a little trick on this because it's a right triangle. It's kind of fun stuff. All right, so draw a right triangle with me. So there is right triangle. Let's go ahead and stick that angle there. And let's call this EFG. All right, so it says if an altitude is drawn to the hypotenuse, so EG is the hypotenuse, remember, longest side of the triangle, opposite the right angle. So if an altitude is drawn to the hypotenuse, then the two triangles formed. Do you see the two triangles? EF, and let's call this H. So EFH and HFG, we will set those up so they're similar. We'll get our letters right. And these two guys are similar to the original. So let's go ahead and write down the original. EFG is my original triangle. All right. So here's what I'm going to do. I'm going to actually, I don't even need that. Let's do something different. Let's pull these apart. All right, so, and let's put them going the same direction. So I am going to redo EFG so that I have the right angle on the left side. So it looks like this. And F is my right angle. So GF is my short side. And FE is my long side, and GE is the hypotenuse. So I rotated this triangle. Everybody see that? We good? All right, now I'm going to take this one. Okay, so here's my right angle on this one, right? If it's perpendicular, it's going to form two right angles there. All right, so let's get this one going. All right, so here's this one. Right angle is H, F, and E. All right, now let's get this last one right here. So I should be able to pick out these similar triangles now, especially since I have them this way. All right, so there's my right angle at H again. GH is the short side, and GF is the hypotenuse, and HF is the long side. So hopefully that makes sense on flipping those around. If it doesn't, make yourself a note. Ask me about it when I see you again. All right, so let's start here. Triangle GFE is similar to triangle FHE is similar to triangle GHF, and all the pieces are also similar. So triangle GFE is similar to triangle FHE is similar to triangle GHF. All right, and we can do that every single time. Get your right angles where they're supposed to be, hypotenuse where they're supposed to be, because here's the deal. The hypotenuse are going to be proportional to the legs and to both legs, both legs. So GF over FH will be proportional to GE over FE, which will also be proportional to GF. So we can make, and GH, we can make all kinds of proportions out of these guys. All right. So let's move on. I have a couple more theorems, and I know we're almost out of time. I know you're watching the clock. I know. Trust me. I've been doing this a while. All right. Right triangle geometric mean. All right, so setting up those similar triangles allows us to move forward with the geometric mean, and this is Theorem 8.2. It's the geometric mean for the altitude theorem. And it says the altitude drawn to the hypotenuse of a right triangle separates a hypotenuse into two segments. All right, now you need to copy this theorem out of your book, and I know you have a book at home because I checked one out to you at the beginning of the year. Probably sleep with it under your pillow because you think it's so awesome, I know. Get that thing out and write down Theorem 8.2. It's on page 533. All right. All right, so there is my right triangle. And it says, the altitude drawn to the hypotenuse of a right triangle separates the hypotenuse into two segments. All right, so here's the altitude. And it's drawn to the hypotenuse of the right triangle. There's my hypotenuse. It separates this hypotenuse into two segments. All right, let's call these X and Y. The length of the altitude, so here's my altitude, let's call this CD. The length of CD is the geometric mean, between the lengths of these two segments. Now we already know how to find the geometric mean, right? So the length of CD, actually let's just call this H. How about that? That means height, which is also altitude. So H, or the altitude, is the geometric mean between these two pieces that it separated the hypotenuse into. So once we draw that altitude, the length of the altitude, or the height of the triangle, is the geometric mean between these two. All right, we'll work a problem like that in just a second. Let's talk about 8.3. 8.3 is a geometric mean leg theorem. Geometric mean leg theorem. All right, let's draw another triangle. Geometric mean leg theorem says the altitude drawn to the hypotenuse of a right triangle separates the hypotenuse into two segments. Yes, we know that, don't we? We are on it. All right, so let's go ahead and label this like we had it before. So there's our two segments. True. The length of the leg of this triangle is the geometric mean between the length of the hypotenuse and the segment of the length of hypotenuse adjacent to the leg. All right, so let's put that in English. All right, so let's say that we're talking about this hypotenuse right here. All right, so actually, it's the leg. It's the hypotenuse of this little one, but this is the leg of the big triangle. So the length of AC, the leg of the big triangle, is equal to the geometric mean between the section, so here's my altitude. So it's equal to the section that's adjacent to it multiplied by this whole thing. So let's call this C, right? So it's equal to the section that's touching it, adjacent to it. We've talked about adjacent sides, multiplied by the whole thing, all the way across the whole hypotenuse. All right, so how do we set up B? So here's the leg. B would be equal to the geometric mean between what? Adjacent side, that's right. So Y multiplied by the whole thing. All right, so we want the product, or multiplying together the adjacent side and then the whole hypotenuse. Then we'll take the square root of that. All right, let's try a problem and then I'm going to let you go. All right, so this is J, K, L. Let's drop this guy down here. This is M. This is 6. This is 24. This is D, and this is C. So I have 6 is this piece, JM. 24 is ML. KM is the altitude. I know that by the picture. And I want to find C, D, and E. So if you'd like to pause the video, and I'll give you some hints as we go, so anytime you want to pause it, please do so. All right, let's put an E on this. So we're looking for C first. So out of the big triangle JKL, C is a side. Here is my altitude. So I know that the leg of a right triangle, the length of that is equal to the one we just talked about, right? This is Theorem 8.2. The side adjacent multiplied by the entire hypotenuse. All right, so talking about the big triangle, JL is the hypotenuse of the big triangle. C is a leg, D is a leg. All right, so this whole thing is 30 because 6 plus 24 is 30. So C is the square root of 24 times 30. The square root of 24 times 30, if you pop that on your calculator, is about 26.8. Now, if we break that down, here's a kind of cool thing. 24 times 30, square root here. This is the square root of 6 times 4 times 6 times 5. Look at this. Perfect square, so I can take a 6 out, so those are gone. Perfect square, I can take a 2 out. The 5 stays in. So 12 square roots of 5. All right, let's talk about D. D is also a leg, so pause the video. See if you can figure this one out without me. All right, now that you're back, and don't just wait on me to say now that we're back, pause the video. All right, so D is the adjacent side 6, sorry, it's a 6. All right, the adjacent side 6 multiplied by the entire hypotenuse, which is 30. So this is, if we multiply together, the square root of 180, but look at this. 30 is 6 times 5. Bam, perfect square again. 6 comes out, 5 stays in. Or, if you pop it on your calculator, it's about 13.4. All right, last one, E. E is the altitude. Remember, the altitude is the geometric mean of the two pieces that it just split into. So 6 times 24. Ooh, this is pretty, isn't it? Square root of 6 times 24. 6 times 24 is 6 times 4. Bam and bam. This will come out as a 6. This will come out as a 2 because the square root of 4 is 2. So we had a pair of 6s, so 1 comes out. You can break this down into 2 times 2, but you don't have to. So that's 12. Or multiply those together and take the square root. All right, so we found all the pieces to this little puzzle. Trust me, I will have more for you when I see you again. This is Coach Lowe, and I'm out.